Another question we may ask when dealing with functions is exactly how bad is the discontinuity? So this is the degree of the discontinuity. So when I say degree of discontinuity, I mean exactly how bad is the discontinuity. And in pictures, we can kind of see what I mean by that. So I think we would agree that this discontinuity is in some sense worse than this one. What I mean by that is, here the function doesn't behave well at all. It has a complete jump. So there's a huge gap going on here. So something weird happens. Here it behaves pretty nicely, actually. The only bad point is at A, at one single point. So in some sense, this gives you a sense of what I mean by the degree of the discontinuity. This is not such a bad discontinuity, because here I can actually redefine the function somehow just to take that one point and paste it in over there. Over here, it's not so easy. I have to almost redefine the function in order to do that. So these have special names attached to them. This is actually what's called an essential discontinuity. And this is called a removable discontinuity. And all I mean is, this is essential in that the function is much less well behaved at my discontinuous point than here. Here it's sort of removable, meaning that I sort of removed one point. That's all I did. And one of the things that we can do is to try to make this continuous by simply redefining the function at one single point. Okay, so let's look at some examples of how we might take a function that is discontinuous and maybe make it continuous, depending on how bad or the degree of the discontinuity. So here's an example. Let's take a closer look. That is, I have a function defined as a rational function here, polynomial over polynomial. And we know this function is perfectly well behaved everywhere except at 2 points, right? The trouble points are at x is -1 and x is 1, right? These are trouble. These points are actually not in the domain of my function. However, I want to see how discontinuous the function really is at these 2 points. That gives me an idea of the behavior of the function. Okay, so I want to investigate continuity of this function near these 2 points that are not in the domain. And maybe if the discontinuity isn't so bad, I can make the function continuous by sort of defining the function at some point, maybe. Okay, so let's take a look. First of all, let's look at this first point here, x is -1. So in order to investigate the function, the behavior of the function nearby that point, let me take limits. So I compute the limit as x approaches -1 of my function x plus 1 over x squared minus 1. And what we get here is that we want to, as usual, work with limits, so we sort of algebraically work with this ratio. So this becomes a limit as x approaches -1 of x plus 1 over this actually can factor into x plus 1, x minus 1. Which means that this becomes the limit as x approaches -1 of 1 over, these cancel, x minus 1. Well, this function is perfectly okay at -1. It's continuous at -1. It's in the domain of this part. So I can actually plug that in. And I actually get 1 over -2, right? Or -1/2. So the key here is, even though in the original function, x equal to -1 is not in the domain, you get, in fact, if I plugged -1 in, that is f of -1 is 0 over 0, right? It's not in the domain. The limit exists as I approach -1. In other words, from both sides, I get the same thing. I get -1/2. So this is a case where the limit exists, but the function doesn't exist or is not defined at that point. So it's missing a value at one single point. So it's fairly well behaved, although not continuous at that point. The key is that I can make it continuous by simply defining the function at that one point. So what I mean by that is, since I know that the function is well behaved, the limit exists, and I know in fact that as x approaches -1, the function will approach -1/2 from both sides, I want to define the following. I want to let f of -1 be equal to -1/2. If I do that, I make the function continuous at the point -1, at the x value -1. Okay? And that's because the discontinuity at -1 was a removable discontinuity. Removable because we saw the limit does exist, although the function is not defined at that point. Okay? It's got a hole in its graph. So then I can just define it this way, and now the function is continuous. So let me write that more clearly here. So originally this is true, but if I simply say, okay, that if I redefine this and say it's equal to this, but in fact it's now equal to -1/2 when x is equal to -1, right? But it's equal to this function everywhere else when x is not equal to -1. If I do that, now the function is continuous at -1. So I've made the function continuous at this x value. Okay? Not only does the limit exist, but I know the limit is -1/2. Moreover, if I define the function to be equal to -1/2 at that point, now I have a function that's continuous there. So again, it was a removable kind of discontinuity. Let's look at the other point. So the other point that gave us trouble was the value x equal +1, right? That also is a trouble point. Let's look at what happens. So again, I'm going to take a limit. So the limit as x approaches +1 of my function x plus 1 over x squared minus 1. Again, I'm going to simplify, just like before, algebraically. Limit as x approaches 1 of x plus 1 over x plus 1, x minus 1. Okay, again, I can cancel as usual. And I get that I have the limit as x approaches 1 of 1 over x minus 1. Problem. 1 is not in the domain of this thing. So I can't just take the 1 and plug it in and know what happens, right? You get 1 over 0, something weird happens. But in order to find the behavior, I need to take these side limits, okay, to really determine what's going on. So let's do that. That is, now again, I'm looking at the side limits to determine the overall limit, the behavior of the function near my trouble point. Okay? So as I approach 1 from below 1, right, I'm just a little bit less than 1. Think about here. We want to know the behavior of this thing. I know that if I get to 0 on the bottom, in other words, what's going on here is as I get closer to 1, the bottom gets really, really small. If the bottom gets very small, but the top stays fixed, the overall function blows up, goes toward infinity. Okay? And so the question, though, is not so much whether it blows up, but what direction. Does it go to positive infinity or negative infinity? So I have to look at signs. So here's the sign. The top is always plus, because it's a 1 up there. As I approach 1 from below, I'm always a little bit less than 1, right? So if I take something less than 1 and then subtract 1 from it, I have something negative always. So this is negative. So overall, this goes off to negative infinity. Similarly, over here, I want to know the sign. Again, as x approaches 1, the bottom gets very small, the top stays fixed, the whole thing blows up. The question is, does it go to positive or negative infinity? Let's look. Here, the top is always positive because it's 1. The bottom, however, is, well, let's look. We are approaching, x is approaching 1 from above, so it's always a little bit more than 1. So if I take something bigger than 1 and subtract 1 from it, I'm always positive, right? So in fact, the bottom is positive. And in this case, the whole thing is positive, so it goes to positive infinity. Therefore, clearly this limit does not exist Moreover, it goes to two different areas. It blows up, it doesn't exist, it's a horrible discontinuity. And in particular, this is a far more serious discontinuity, right? This discontinuity is called an essential discontinuity. And there's nothing I can do to actually fix this discontinuity here. In other words, it will blow up. There are no points that I can actually define to magically make this function continuous. So let's write down our results. So summarizing, I have defined a new function here. In some sense, it becomes a piecewise function. Really, it's only defined as -1/2 at one single point. But the key is that it had a removable discontinuity at x equal -1, removable in the sense that the limit exists, it just didn't take on a value at that one point. That one point was not in the domain of the function. And I made the function continuous by simply doing that. So it had a removable discontinuity, I took care of it, now it is continuous there. And we saw that it has an essential discontinuity at x equal +1, because we saw the limit doesn't even exist there. Okay, so this new function that I've created actually is continuous because it has a removable one. It's continuous now at x equal -1 because I sort of forced it to be that way. But it's still discontinuous at +1.